We're now going to take a look at systems of equations from the point of view of their solutions. And referencing their solution sets, systems of equations can be put into three different classes: consistent systems, inconsistent systems, and dependent systems. Consistent systems are systems which have one solution. That doesn't mean the solution is one number. If the system is a system with three unknowns, then the solution will be a triple. The 5, -1, and 3, something like that, where x is 5, y is -1, and z is 3. That's if it's three variables. If it's four variables, you'd have a four-tuple. But it is one solution. That single triple is the single solution to the system. That's if the system is consistent. An inconsistent system, on the other hand, has no solutions at all. And then the third classification would be dependent systems, which have infinitely many solutions. Now, before we begin looking at each type system, I want to recall the concept of an equivalent equation. Two equations are called equivalent or dependent if one equation is a multiple of the other. And when that happens, both equations will have the same solution set. So this pair right here is a pair of equivalent or dependent equations because I can get the second equation by multiplying all the terms of the first one by -2. Go ahead and check that out for yourself. And so what that means is, since they're dependent or since they're equivalent, it means the solution set of the first equation and the solution set of the second are the same. Okay, let's take a look at our different types of systems now. How do you recognize when you have a consistent system that's going to have one solution? Imagine we had a system and we're trying to put it in Gaussian form. And we've been successful. We've made our row of ones down the main diagonal with zeros below. You can look at this system and you can see from its structure that it is going to have one single solution, because you can actually sit here and in just seconds compute what that solution is. The last equation says 0x plus 0y plus 1z equals 3, so that just means 1z is 3 or z is 3. The second equation says y plus 1z is -1. Well, if z is 3, that means y plus 3 is -1, or y would be -4. And the first equation says x, or 1x, plus 3y, I didn't mean to put a y there, plus 3y plus 1z equals -2. If I put in my 3 that I got for z into the z hole, and if I put the -4 I got for y into the empty hole for y, I get x plus -12 plus 3, or x minus 9, is equal to -2. If I take the -9 and take it to the other side, it becomes +9, so a +9 minus 2 would be a +7. And so not only does it have one solution, but you can instantly from the structure see not only the solution but how you get it. Now, if you take this one step further, there's a more advanced form than Gaussian form, but it's based on all the same operations. If instead of starting up here and making your ones this way, you start down here after you've already achieved Gaussian solution, and you start moving up this way, making zeros above, you get this kind of structure where you still have ones down the main diagonal, but now there are zeros above and below, and that's called a Gauss-Jordan form, or reduced form. And when you've got your system in reduced form, it's very clear that it's consistent, because you can just read the solution right off that back row. In other words, the first equation says x plus 0y plus 0z equals 7. That tells you x is 7. The second equation says 0x plus y plus 0z is -4. So since the x and z were zeros, that just says y is -4. And similarly, the last one says z is 3, and you can read the thing off and see immediately that you have one single solution, and therefore that's a consistent system. Now, the second type, or the second classification of systems of equation, is called an inconsistent system. And in the inconsistent system, you get no solutions, and there's a couple of ways that can happen. The first way is if you're proceeding along with your Gaussian reduction and you've made your 1 and you got your zeros below and you've made another 1 and you go to get your 0 below and bingo, you get a weird looking equation like this, where you got zeros all to the left of your equal sign and a non-zero to the right. This equation is impossible to solve because it says 0x plus 0y plus 0z equals 3. The only thing 0x plus 0y plus 0z can equal is 0. So this is an impossible equation to solve, and since a solution to a system has to solve every one of the equations in the system, and this equation can't be solved, that means there are no solutions to the system. And you could see that no matter what I try to put into that third equation, let's say I put in a 10 and a -7 and a 4, I still am making a 0 plus a 0 plus a 0, so it can't possibly be 3. So one way to identify an inconsistent system quickly is just to see if there's an impossible equations. That's zeros to the left, a non-zero to the right. And it doesn't have to be in the last row, it could be in the middle row. If there's an impossible equation anywhere, no solutions. Here's another way that you could get no solutions. In this system, I have 3 independent equations. I can kind of see that they're independent because I can see that no multiple of the middle one could produce the top one or the bottom one. No multiple of the bottom one could produce the middle one or the top one, etc. So these are 3 independent equations and only have 2 variables, x and y. When you have more equations than variables, you're always going to generate, in the process of trying to put it into Gaussian form, you're going to generate an impossible equation. Let's see how that would be done here. Let's switch these first 2 rows to get my lead 1 started. Then that would put the 4, 1, 2 here and the 2, 3, 1 here. And now let's start making zeros. I'll do -4 row 1 plus row 2 into row 2 and -2 row 1 plus row 3 into row 3, and here will be the results. In row 2, -4 row 1 puts a -4 plus 4 here. -4 plus 1 is -3 here. -4 plus 2 is -2 here. In the -2 row 1 plus row 3, -2 times 1 is -2 plus 2 is 0, -2 plus 3 is 1, and -2 plus 1 is -1. All ones across the top. And then I could get my 1 in the second row if I just switch these 2 rows around. So I'd have 1, 1, 1 on the top, 0, 1, -1 for the second row, and 0, -3, -2 for the third row. And now you can see the problem. If I do 3 row 2 plus row 3, look at what my row 3 is going to be. 3 times 0 is 0 plus 0 is 0. 3 times 1 is 3 plus -3 is 0. There's your all zeros to the left. And 3 times -1 is -5 plus -3 plus -2 is -5. And there's that impossible equation. So you get no solution. So there's 2 basic tip-offs to inconsistent system. You'll either see an impossible equation, zeros to the left, non-zero to the right, or you'll see more equations, more independent equations than you have variables. And that was the case here. Now let's take a look at the last type of system we have. That's the system with infinitely many solutions. That's called a dependent system, and it's the opposite of what we had here. Here the number of independent equations was greater than the number of variables. In the dependent system, you're going to have that the number of variables is greater than the number of independent equations. It's the exact opposite of case 2. So here I have 3 variables, x, y, z, but only 2 independent equations. Now you say, well, isn't that third equation independent? Well, it's kind of independent, but it's what we call a trivial equation. It contributes nothing to the solution, because no matter what ordered triple you put here, you're going to get 0. 0 times x plus 0 times y plus 0 times z is always 0, so that doesn't really tell you anything about solutions. So basically you're limited here to 2 independent equations, and you have more variables than equations. Now when you get the infinitely many solutions case, which is this case, we generally give our solution in parametric form. First we set up a parameter. That's just a variable which can take on any value. So if I set up, say, the parameter t, I start off my solution by letting z be t, and I'm trying to give a solution x, y, z. So z is t, so there's my z. I then go to the 2 equations that I have in this case. The second one says y minus 2z equals 3, but z is t, so I put that in there. So for my t, I get for my y, I get 2t plus 3. And then for my x, I have x minus 3y plus 1z equals negative 1. For my z, I put in my t. For my y, I found that y is 2t plus 3, so I put that in here. So I end up with x, and here's a minus 6t here with a plus 1t here, so that's going to give me minus 5t minus 6 equals negative 1, so x equals 5t plus 5. And there is my solution set, and that is the set of answers for all t. That's why it's infinite. You can let t be anything and you get a solution if it follows this pattern. So for example, if t equals 1, this leads to the solution 5 times 1 plus 5, which is 10, 2 times 1 plus 3, which is 5, and then t is 1, so 1. So you get the solution 10, 5, 1, and that will solve all the equations in the system. So as a quick recap, consistent systems, one solution. You can usually tell it from its structure. If you reduce it to Gaussian form and you still have the same number of equations as you have variables, in this case 3 and 3, you've got a consistent system with one solution. In consistent systems, you're looking for that impossible equation. If you either have an impossible equation or you have more equations, in this case 1, 2, 3 equations and only 2 variables, that's going to lead you down to that impossible equation as you try to pursue your Gaussian solution. And then dependent systems is the opposite of inconsistent. Instead of the number of equations being greater than the number of variables, the number of variables is greater than the number of independent equations, and so you get infinitely many solutions, which we write in parametric form. Those are the types of systems that we study, and that concludes the podcast.